Okie dokie, folks. One topic left. Going to take 3 days to talk about it. And when we're done with this topic, we're done with AP Calculus BC. Polar functions. Got to remind us of everything we used to know about polar functions, polar coordinates. Some of it is familiar from a pre-calculus course. Others of it will not be, but that's okay. So if I stuck a point in 2 space and said, where is it? You would do this. You would say, I'm going to come out from the origin some distance x, and I'm going to go up some distance y, and so the coordinates of that point are x, y. And these are, in fact, rectangular coordinates. Those are rectangular coordinates because the rectangular grid is based on, you guessed it, rectangles. So what happens if we decide to turn the system on its head? What happens if we say, I'm not going to go over and up, I'm going to go out some distance r, a radius if you will, and I'm going to rotate some angle theta with respect to what used to be called the positive x-axis, but is now called the pole. Well, if that's the case, then the coordinates of our point are r theta, and they are called polar coordinates. In a polar coordinate system, we measure out from the origin and around the pole rather than over and up. Now, that creates some issues because there are many thetas for a given point, because you can just spin around 2 pi or negative 2 pi, just keep spinning, just keep spinning, just keep spinning, 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 and you never go anywhere. Likewise, for example, if this were the point, and I'm just making something up off the top of my head, if this were the point 2 pi over, probably pi over 6 more than it is pi over 3. If this is 2 pi over 6, it is also the same as negative 2 7 pi over 6. Because if I started at negative 2 on the pole, I would have to rotate counterclockwise 7 pi over 6 to get there. Okay? Okay. So, play with a couple of points. Let's find rectangular coordinates for 4 pi over 2, 16, 5 pi over 6, negative radical 2, negative pi over 4. Make sure we can go from one to the other. 4 pi over 2. That means we come out a distance of 4 from the origin at an angle of pi over 2 from the positive pole. So if this is the point 4 pi over 2, then, well, how do we get there rectangularly? We don't go across at all. We go up 4. That's the way this goes. Similarly, if we were looking at an angle of 5 pi over 6, this figure is totally not drawn to scale. 5 pi over 6, really? 5 pi over 6 in the second quadrant. Yes, yes it is. 5 pi over 6. It's out here somewhere. That's 5 pi over 6. That's 1 pi over 6. This radius has length 16. You could do a little bit of trigonometry and figure out we're going left 8 radical 3 and up 8. This is the standard 1, 2 radical 3 right triangle, and you could get rectangular coordinates that way. Last but not least, If I'm at negative radical 2 on the pole and I rotate negative pi over 4 degrees, that's a clockwise rotation. This radius is radical 2 in its length, and so that tells me that I went left 1, up 1 to get there. Generally speaking, if I want the x coordinate and I know the polar coordinates, that is r times cosine theta. The y coordinate is r times sine theta. Those are things you need to tuck away. You need to have those at your disposal at all times. Why does that work? Well, we take the generic point, x, y, theta, r. If you know that picture, then you know when I'm looking for this right here, oh, let's do it this way, this right here, how do I get that? Well, x over r is cosine theta, so a little cross multiplication gets me what I want, and similarly for y. So there are some graphs that you ought to know about. There are some graphs rather that you ought to know about. So let's see. If I want to graph r equals 3, I want to graph all those points that are 3 away from the origin. All those points that are 3 away from the origin. Oh, wait, here they all are. This is r equals 3. As a side note, this is also r equals negative 3, just as a quick aside. Theta equals pi over 3. All the points that are at an angle of rotation of theta equals pi over 3. Well, that would be all of these points if r is positive, and all of these points if r is negative. So this is theta equals pi over 3. As a side note, this is also theta equals, well, we can just spin around pi forever. This is also theta equals 4 pi over 3, theta equals negative 2 pi over 3, and so on. But what if things get just a little bit more ridiculous? What if I want to graph r cosine theta equals r sine theta? Well, then I've got to go back to basics and remember that on the last slide I saw that r cosine theta was x and r sine theta was y, and so you get this line. And that's the only line you get. There are some other pictures with which you should be familiar. We do not have time to develop them in this video series. However, a good pre-calculus textbook is going to do that. One is what we call the Rose curve. One is what we call the limison, from the old French word for snail. And one will just be, hopefully, blunt obvious when we do it. So, I'm getting ready to take pictures. Where are you, calculator? Where did you go, calculator? Hello, calculator. So when you graph in polar mode, you actually have to go into polar mode. And then what happens? Well, you want to graph sine of 6 theta. The xt theta n button cranks out thetas. And so you hit graph, and it's not very helpful at all. And so you zoom in, and that's a little bit more helpful. And you square the window, and that's a little bit better. Can I get this better? square that. No, that didn't help. -1.5 to 1.5. That's a little bit ugly, but less so if we square the window. Oh, really? I'll zoom in for a moment so you can see it. Looks like that. It looks like that. It's got petals. It's got petals. It is a 12-petaled rose. In fact, anything of the form A sine B theta is going to be a 12-petaled rose. I'll show that to you a little bit more clearly by multiplying by 2. That's a little better. Here, we'll take a picture of that. That's a little better. Yes, 2 sine 6 theta. Every petal has a length of 2. There are 12 evenly spaced petals all around the origin. Secondly, 1 minus 2 cosine theta. Looks like this. It's from the old French word for snail for obvious reasons. This is a limison. It's a limison because it's got that little curly Q in the middle that looks like a snail. If I were to change things, just a scotch, if I were to go with a 2 minus a 1 instead, I would get something that, really? Let's try 3 minus 2, make it more pronounced. Nope, that doesn't help. That really doesn't help. I would get something called a cardioid. I would get something that looks like a cardioid, because it looks like a heart. When the absolute value of B is less than or equal to the absolute value of A, when the absolute value of this number is less than or equal to the absolute value of this number, I get something called a cardioid. You'll be able to know that because it looks like a heart. And then lastly but not leastly, 4 sine theta, there it is. There it is. That's not very helpful. So we're going to go from negative 0.5 to 4.5. That's better. And I think we know what that is right off the bat. That thing is a circle. This thing is a circle whose diameter is on the positive y-axis and whose diameter is of length 4. So those are all things from our work last year that you should be very, very familiar with. You should know what equations are going to lead to what pictures. That's just, we've got to know it. Okay, fantastic. Now, the next lesson will be all about, super, I can graph this thing, but how do I find its slopes at various places? And so that's what we'll talk about when we get together next time. All right.